Relativity is a magnificent equality principle of nature at creating the universe. However, it has many counterintuitive, mind-blowing concepts, and many of us may have a hard time at understanding it. How could light propagate in vacuum without a media? How could the speed of light remain constant for all observers? Why there are time dilation, length contraction, and loss of simultaneity? Why the laws of nature remain the same for all moving frames? How could space and time be bent by mass and energy? Are our brains wired in such a way so that it is always difficult to understand relativity in a natural way? Or there may exist a new knowledge framework, and a new representation so that relativity become easier to be understood. This video offers the mechanical approach for the first time to explain relativity. It attempts to make relativity easier for the general public to understand. There are lots of books, videos, and slideshows on relativity with stories of spaceships, trains, lasers, and moving light clocks and light rulers. However, people are still confused by the theory generation after generation. After reading a whole stack of those books, many of them don't understand why light can propagate in pure vacuum without any medium, why the speed of light is magically constant, why a moving clock is slower and a moving ruler is shorter. And most importantly, how could the laws of physics remain the same for all uniformly moving frames? Relativity says that light can travel in vacuum without any medium. However, this statement is just the emperor's new clothes in the theory. It mystifies the propagation of light. It is also bluntly against our intuition. There is no way for any wave to propagate in space without any medium. Permittivity and permeability are not the properties of space. It makes no sense to assign those physical properties to space. Rather, they are the properties of the medium for propagating electromagnetic waves. All waves need a medium to propagate in reality, including light. In relativity, it has often been argued that light travels at a constant speed because it propagates in vacuum as waves without the need of any medium. It has been treated as a genius idea at solving the puzzle of the constancy of the speed of light. However, such a reasoning is also the emperor's new clothes in relativity. This statement mystifies the constancy of the speed of light, making it unfathomable. It sounds more like a magic than a logic statement. Also, it is logically incorrect to postulate a statement, such as the constancy of the speed of light, to prove the statement itself in a circular way. What we need here is a true mechanical explanation for the constancy of the speed of light, if it is true in reality, without mystifying it. There is a critical logic error in relativity theory. To be more specific, the constant speed of light should not be treated as the second key postulate of relativity. The fact is that relativity holds true regardless of whether or not the speed is constant. This postulate is simply redundant for the theory. It is the biggest misconception in the theory, confusing almost everyone including Einstein. Two key postulates in relativity. Postulate number 1. The laws of physics remain the same for all uniformly moving frames. Postulate number 2. As measured in any inertial frame of reference, light is always propagated in empty space with a definite velocity c that is independent of the state of motion of the emitting body. There are two important logical consequences from the first postulate. Consequence number 1. All free objects must share exactly the same maximal speed limit. Otherwise, the principle of relativity is violated. Consequence number 2. If a particle travels at the common maximal speed limit in one inertial frame, it must travel at the same speed in all inertial frames. That is, its speed is constant in this case. The second postulate is redundant. We can see that the constancy of the speed of an object is a logical consequence of the first postulate. There is no need to postulate the constancy of the speed of light. Using it as the second postulate to explain relativistic effects such as time dilation, length contraction, and loss of simultaneity could be confusing to the general public. Oftentimes, people mistakenly thought it is the cause of those relativistic effects. However, the truth is that we have those relativistic effects as long as the common maximal speed limit is of a finite value. In other words, we suffer from time dilation and length contraction as long as the common maximal speed limit is of a finite value, regardless of whether or not the speed of light is constant. We only need the first postulate for relativity. That is, we only need to postulate the principle of relativity, first proposed by Galileo Galilei, then further extended by Henri Poincaré to all laws of physics. There is no need to have the second postulate. The constancy of the speed of light is not only a redundant postulate, but also an inaccurate statement about reality. In the real world, the photon never moves like a point object with a definite position at any given time instance. Instead, it moves like a wave without a definite position at any given time governed by quantum laws. The light clocks and rulers used in the classical relativity thought experiments never exist in reality. They only exist in our imaginations. Simply put, those thought experiments are wrong in terms of physical reality. With the same argument, the classical motion equation for light, c squared times t squared minus x squared equals 0, where the photon is treated as a classical point object, is also incorrect. It should not be used to derive the Lorentz transformation, a key transformation in relativity. The constant speed of light should be a hypothesis subject to experimental verification. Up to now, nobody is sure about the constancy of the speed of light. Neither the Maxwell's equations, nor the Michelson-Morley experiment can tell us the constancy of the speed of light because they are not exactly accurate. Recently, it has been found that spatially structured photons in free space travel slower than the speed of light. Vacuum isn't really empty, but is filled with virtual particles. A virtual particle pair can pop out of the vacuum for a very short time interval then disappear. Light will interact with those virtual particles. At present, nobody knows if the interaction with virtual particles in vacuum will slow down light from its maximum speed limit. Space-time metric should not be treated as fundamental concept in relativity. It has been used as the fundamental concept both in special relativity and general relativity. However, the concept is valid only at the classical limit. It works only for computing the trajectory of a classical point-like object. It doesn't work for quantum particles which behave more like waves than point-like objects. Special relativity has been established around 1905 and general relativity is around 1915. Both of them are more than a decade ahead of the establishment of quantum theory. All the concepts used in relativity are classical ones. For example, objects have definite position and velocity at any time instance. Each object has a definite trajectory in space-time. However, those pictures are inaccurate, oftentimes misleading in the quantum world. You cannot simply treat an atomic system as a solar system because each electron of the atom doesn't have a definite orbit. Rather, it has a cloud of probability. It is desirable to reconcile relativity with quantum theory. The fundamental reason for relativity remaining as a mystery is because the mechanical explanation for it is missing so far. Without it, relativity remains as a mystery and a magic of nature, hard to be understood by human brains. It is time to offer a mechanical explanation for relativity based on quantum theory. To come up with the mechanical explanation for relativity, let us start from the Standard Model. Based on the Standard Model, the most successful theory of particle physics, if the Higgs field did not exist, all elementary particles would travel at the speed of light. Some of elementary particles interact with the Higgs field to have rest mass and slow down to any speed below the speed of light. The ones which do not interact with the Higgs field will always travel at the speed of light. In quantum field theory, elementary particles are excited states of the underlying physical field, so-called field quanta. For example, electron field generates electrons and electromagnetic field generates photons. As mentioned before, to have the principle of relativity, all particles must share exactly the same maximal speed limit at any position of space and at any time. If there is any slightest difference in the maximal speed limit for different particles, the principle of relativity is violated. To resolve the mystery, the author postulates that all elementary particle fields are different manifestations of a more fundamental field, traditionally called the ether. Different particles correspond to different excited states of this fundamental field, so that they have different spins, charges, colors, and masses. It is postulated by the author that, at the most fundamental level of nature, everything is made of particle waves and field waves. All of those waves are different excited states of a fundamental medium, traditionally called the ether. Those waves, either free ones or coupled ones, are propagating in space with the same pattern defined by a quadratic partial differential operator g mu nu partial nu. In relativity, g mu nu partial nu is a shorthand notation for the summation with respect to mu from 0 to 3 and the summation with respect to nu from 0 to 3 g mu nu partial nu. Where partial mu is a shorthand notation for partial derivative with respect to variable x mu. As a convention, x0 equals t, x1 equals x, x2 equals y, and x3 equals z. T is the time coordinate, x, y, z are our spatial coordinates. When there is no gravity, it has been found in quantum mechanics that the propagation of particle waves and field waves are governed by the following operator. -1 divided by c squared times partial t square plus partial x square plus partial y square plus partial z square. This operator is oftentimes denoted as box, called the D'Alembert operator. In particular, for any free particle, either a boson or a fermion, it satisfies the Klein-Gordon equation as D'Alembert operator on the particle wave function psi xyzt equals m squared times c squared divided by h bar squared times the particle wave function psi xyzt. Here, m is the mass of the particle, c is a constant defining the maximum speed limit for all particles, and h bar is the reduced Planck constant, one of the most important constant in physics. Electromagnetic waves can be imagined as a self-propagating oscillating wave of electric and magnetic fields. In general, an electromagnetic field can be represented by a four-component vector field called an electromagnetic four-potential field, denoted as a xyzt. When there is no gravity in a vacuum space, it satisfies the following wave function. -1 divided by c squared times partial t square plus partial x square plus partial y square plus partial z square a, xyzt, equals 0. That is, the propagation of the electromagnetic four-potential field is governed by the D'Alembert operator. Using the universal wave propagation operator g mu nu partial nu, the Klein-Gordon equation can be simply generalized to g mu nu partial nu times the wave function of a particle psi, xyzt, equals m squared times c squared divided by h bar squared times the wave function of the particle psi, xyzt. It has been proven by the author that the above generalized wave equation falls back to Einstein's geodesic equation in general relativity at the classical limit. Einstein's geodesic equation is used to compute the trajectory of a point-like object in a curved spacetime with its metric as g_mu nu. The wave equation at the top is more general than Einstein's geodesic equation because the latter is only the classical limit of the former. Based on the previous investigation, we can conclude that the universal wave propagation operator g mu nu partial nu manifests itself as the spacetime metric g_mu nu dx mu dx nu at the classical limit, where the covariant metric tensor g_mu nu is the inverse of the contravariant metric tensor g mu nu. Simply put, the geometry of spacetime is a result of the propagation of quantum particle waves in space and time. As a summary, we have the universal wave propagation parameters g mu nu where mu and nu equals 0, 1, 2, 3, define the geometry of spacetime with the spacetime metric as g_mu nu. The spacetime metric g_mu nu dx mu dx nu is a fundamental concept in both special and general relativity. From the previous investigation we can see that it is only the classical limit of the universal wave propagation operator g mu nu partial nu. At the most fundamental level of nature, everything are just waves. Therefore, the wave propagation operator is more fundamental than the spacetime metric. The latter belongs to classical physics, valid only when every object can be treated as a point object with a definite position and velocity at any given time. The universal wave propagation operator g mu nu partial nu is more fundamental than the spacetime metric g_mu nu dx nu at understanding relativity. Einstein suggested that gravitational potential is defined by the spacetime metric g_mu nu. Whenever there are variations of g_mu nu, it causes gravitational acceleration. The variations of g_mu nu are caused by the presence of matter and energy and others defined by Einstein's field equation in general relativity. Since g mu nu is more fundamental than g_mu nu, the author hypothesizes that gravitational potential is defined by the universal wave propagation parameters g mu nu, instead of the spacetime metric g_mu nu as suggested by Einstein. At any point of spacetime, the propagation operator g mu nu partial nu can be normalized to the standard form as -1 divided by c squared times partial t squared plus partial x squared plus partial y squared plus partial z squared and remains the same after the Lorentz transformation. That is exactly the reason why laws of physics remain the same regardless of gravity, and the relative motion of an observer. This is a mechanical explanation for relativity. In particular, to any observer at his local space, every hydrogen atom, water molecule, protein, or any other atoms or molecules remain the same in their structures and properties regardless of the gravity and motion of the observer. Otherwise, life is impossible. The author concludes that we have relativity simply because the universal wave propagation operator g mu nu partial nu is normalizable to -1 divided by c squared times partial t squared plus partial x squared plus partial y squared plus partial z squared and remains invariant under the Lorentz transformation. It is an elegant design of nature because there is no way for laws of physics to remain the same regardless of gravity and motion if the universal wave propagation operator is not of the quadratic form g mu nu partial nu or the propagation operator g mu nu partial nu is not shared by all particles. The second condition is the reason for the author to postulate that different elementary particles are propagating in the same medium as different excited states. Simply put, we have g mu nu partial nu equals relativity and gravity. There is a very important property for the universal wave propagation operator. It is invariant in form under the Lorentz transformation shown as follows. The original universal wave propagation operator. The Lorentz transformation applied to the spacetime coordinates. The new universal wave propagation operator after the transformation with the new spacetime coordinates. Note that it has the same form as the original one. Note that the Lorentz transformation is defined as x prime equals gamma times x minus v times t. Y prime equals y. Z prime equals z. And t prime equals gamma times t minus v divided by c squared times x. Where gamma equals the inverse of the square root of 1 minus v squared divided by c squared, called the Lorentz factor. The Lorentz transformation defines a linear transformation from the spacetime coordinates x, y, z and t of the original frame to the spacetime coordinates x prime, y prime, z prime and t prime of a new frame. Note that the spatial origin of the new frame is v times t, 0, 0 in the original frame. That is, the new frame is moving with the constant velocity v with respect to the original one. The two frames are in relative motion with the velocity v. The author concludes that the invariance of the universal wave propagation operator in its standard form under the Lorentz transformation is the actual cause for the principle of relativity to hold true in nature. It is a mechanical explanation for why laws of physics remain the same for all uniformly moving frames. That is the essence of special relativity. The spacetime metric of classical special relativity is: it is a manifestation at the classical limit of the universal wave propagation operator in its standard form. Therefore, the essence of special relativity is the invariance of the universal wave propagation operator in its standard form, not the symmetry of spacetime. The wave propagation is more general and fundamental than the spacetime metric. The true reason to have the Lorentz transformation is the invariance of the universal wave propagation operator under this transformation such that the relativity principle holds true. If we use a computer program to simulate any physical process using the universal wave propagation operator at the lowest level, and to simulate the observations of the process in different frames, we always find that the spacetime coordinates of different frames satisfy the Lorentz transformation. There are many ways to derive the Lorentz transformation from other conditions, such as the constant speed of light, plus the homogeneity of space and time plus the isotropy of space and plus the relativity principle, or the invariance of the spacetime interval. Delta S square equals c square times delta t square minus delta x square minus delta y square minus delta z square. However, those are purely mathematical ways that build up logical connections and equivalence among different mathematical statements and equations, not causality in physics. In mathematics, it is also perfectly fine to say that we have the constancy of the speed of light because spacetime satisfies the Lorentz transformation. Simply put, mathematical equivalence does not equal to physical causality. The Lorentz transformation is not caused by the constancy of the speed of light. This is an example of the right answer but for the wrong reason in physics. It simply doesn't matter whether or not the speed of light is constant to have the Lorentz transformation. Inverse Lorentz transformation can be obtained simply by exchanging the spacetime coordinates as x switches with x prime, y switches with y prime, z switches with z prime, and t switches with t prime, and replacing the velocity v by negative v because the two frames are moving in an opposite direction relative to each other. Specifically, we have x equals gamma times x prime plus v times t prime. Y equals y prime. Z equals z prime. And t equals gamma times t prime plus v divided by c squared times x prime. As postulated here, all particles are excited wave packets of the same medium. In reality, no matter how stiff the medium is, the maximal speed limit must be finite. That is the exact reason why light has a speed limit. So are other particles. This can also be explained using the Klein-Gordon equation mentioned before. Because all particles satisfy the equation as: here, m is the mass of the particle, c is a constant. When m equals 0, then the speed of the particle wave is the constant c in the equation. When m is greater than 0, from the equation at the classical limit, the speed must be any value less than c, including the value 0. That is, the particle can be at rest when it has a mass. As revealed before, in order to have the laws of physics remain the same, the spacetime coordinates of the moving frame and those of the original one must satisfy the Lorentz transformation as a constraint. This has manifestations on the measurements related to space and time. The examples are relativistic speed addition law, the constant speed phenomenon, time dilation, length contraction, and loss of simultaneity. They are called the relativistic effects. When time and space are defined by the Lorentz transformation, the classical speed addition law, u equals u prime plus v, is no longer valid. Instead, It should be replaced by relativistic speed addition law. Assume that there is an object with its measured velocity in a moving frame as ux prime, uy prime, and uz prime. Then its velocity in the stationary frame can be discovered using the Lorentz transformation as follows. From the relativistic speed addition formula, we can understand the mystery of the constant speed of light. From the relativistic speed addition formula, it is straightforward to prove that if an object is moving at the speed limit c in one frame, then its measured speed in any other frames is always c. That solves the mystery of the constant speed of light. Specifically, if light is traveling at the speed limit, then its speed remains the same in all frames. Otherwise, if light is traveling at a speed less than the speed limit c, then the speed of light cannot be constant. From the formula, we can also see that c is the maximal speed limit for all particles in nature. No matter how long you add up speed for an object by acceleration, c is its maximal speed limit. Its speed can be arbitrarily close to the limit, but never reach the limit. Whenever we change the state of a clock from stationary to a steady motion, it appears to slow down in ticking rate. If we jump to the frame moving together with the clock, it restores the original ticking rate. This called time dilation. Time dilation can be derived mathematically from the Lorentz transformation. For a clock stationary in the second frame x prime, y prime, z prime, and t prime, let the elapsed time be delta t prime. Since it is stationary in it, we have delta x prime equals 0. From the inverse Lorentz transformation, we have delta t equals gamma times delta t prime plus v divided by c squared times delta x prime. It equals gamma times delta t prime. Since the Lorentz factor gamma is greater than 1 when the velocity v is not 0, we have delta t is greater than delta t prime. Time dilation is mutual. Assume there are two identical clocks in relative motion. Then to each clock, the other clock appears to run slower than itself. There is a key point at measuring length in relativity. To measure the length of a ruler, either stationary or moving, the key point is to take down the coordinates of the two endpoints of the ruler at the same time and subtract them to get the measured length. Whenever we change the state of a ruler from stationary to a steady motion, it appears to be shortened along the moving direction. If we jump to the frame moving together with the ruler, it restores the original length. This is called length contraction. Length contraction can also be derived mathematically from the Lorentz transformation. For a ruler stationary in the second frame x prime, y prime, z prime, and t prime, let its length along the x prime axis is delta x prime. Since we measure its length at the same time in the first frame, x, y, z, t, we have delta t equals 0. From the Lorentz transformation, we have delta x prime equals gamma times delta x minus v times delta t, that equals gamma times delta x. That leads to delta x equals delta x prime divided by gamma. Since the Lorentz factor gamma is greater than 1 when v is not 0, we have delta x less than delta x prime. Length contraction is also mutual. Assume there are two identical rulers in relative motion. Then to each ruler, the other ruler appears to be shorter than itself along the motion direction. If we use a computer program to simulate any clock or ruler using the universal wave propagation operator at the lowest level, we always get time dilation, length contraction, and any other relativistic effects. Time dilation and length contraction are not caused by the constancy of the speed of light. This is another example of the right answer but for the wrong reason in physics. It simply doesn't matter whether or not the speed of light is constant to have time dilation and length contraction. The most important work on relativity theory has been done in history by Galileo, Newton, Michelson, Lorentz, Poincaré, Einstein, and Minkowski. There were also contributions by Voigt, Fitzgerald, and many others. This presentation is just an attempt to make it easier for the general public to understand the fascinating theory.